In this video, I'm going to show you some additional examples of hypothesis tests for a population mean run on the calculator. And I'm going to be getting some examples from section 10.3 in the book. Probably a good call if you join me. I'm looking at page 548 right now, and that's where I'm going to get my first example from. If you recall, when you don't know the population standard deviation, it's considered appropriate to use the t-distribution in order to test a hypothesis of this type. So that's what we're going to be using, and the t-distribution is found in the stat menu under the test submenu, and it's right there underneath the z-test. It's number 2, the t-test. Now for this first problem, I'm reading number 18 here. It says normal temperature. Again, this is problem 18 on page 548. Carl Reinhold August Wunderlich said that the mean temperature of humans is 98.6 degrees Fahrenheit. Researchers measured the temperature of 26 females 1 to 4 times daily for 3 days to get a total of 123 measurements. The sample data yielded a sample mean of 98.4 degrees Fahrenheit and a sample standard deviation of 0.7 degrees Fahrenheit. Now in this problem, they plainly state that the standard deviation is from the sample and not from the population. It's not always stated so clearly. You have to learn how to read the language of the problem and be sensitive to when they tell you, it's a sample standard deviation as opposed to population. Anyway, part A of the question says, using the classical approach, judge whether the normal temperature of women is less than 98.6 degrees Fahrenheit at the alpha equals 0.01 level of significance. Now, when you're getting started doing hypothesis testing, it's a good idea to actually draw the distribution, to draw the rejection region, to label everything appropriately, and so on. I'm not able to do that on the screen here, so I'm just going to use the calculator. But when you read this here, the first thing we want you to notice is that the alternative hypothesis is given there in English. It says, judge whether the normal temperature of women is less than 98.6 degrees. So that there is the alternative hypothesis, and that's a left-tailed test. Now the first thing you need when you do the classic approach is the boundary value for the rejection region. And there are 2 ways to get that. You can go to the t-table, which is in the back of the book or on the formula card. And if you use the t-table, the first thing you probably notice is that there is not a row for 122 degrees of freedom. So that means you have to approximate the value using the next value below that. It gives you a more conservative result. And so you would round that down to 100 degrees of freedom, and that is found in the table. You can also use the calculator to get that value. You can go to the distributions menu, and the calculator has an inverse t distribution here, which is similar to inverse norm. And so you could select that, and if you know what to put in this case you would put in the tail area, which would be alpha, so 0.01, and the degrees of freedom. Then the calculator will give you the boundary value. So in this case it's negative 2.357 and some change. Now I don't want to write that down. I don't have anything to write on here, so I'm just going to stash that in a memory register for future reference. Let's put it in memory register A. And so it's there now. I can get it back later without having to redo the calculation. So the next thing we would want would be the test statistic. And you could calculate it by hand, but the calculator will give it to you. So we might as well just get it that way. We're going to want it anyway. Go to the stat menu, go to tests, and we want to use the t-test, number 2. Now we need to use sample statistics for this one, so we'll change that to statistics there. And what do we need to put in? Well, mu naught, if you recall, is the value of mu according to the null hypothesis. So in this case that would be 98.6. That's the status quo. And x bar is given to be 98.4. S sub x is the calculator's notation for sample standard deviation. It's given in the problem as 0.07. So 0.7. And then the sample size is needed. It gives it degrees of freedom. So n was 123. Now the alternative hypothesis is for a left-tailed test. So we would want to select that. And then we want to calculate. And so the test statistic is right there. It's negative 3.1687, blah, blah, blah. And in the classic method, When the test statistic lies inside the rejection region, as it does here, we would then reject the null hypothesis. Now, of course, you can see that right here because the p-value is given, and it's incredibly small. It's 0.000967 and some change, and that's most definitely less than alpha is 0.01. So on that basis, we would also reject the null hypothesis, and that's what the problem is asking here in Part B is, or well, actually, it's not. It's asking us to determine and interpret the p-value. Well, there's the p-value right there, and the interpretation is given at various points throughout the book. Basically, the boilerplate interpretation of that would be that the probability, assuming the null hypothesis is true, the probability of obtaining a test statistic more extreme than the one we obtained is that value right there, 0.000967 and some change. So a very small probability, and that basically suggests that the null hypothesis is false. Now for the next example, got another problem here from the same section. It's on page 549. It's number 22. This is a data-driven problem. It says reading rates. Michael Sullivan, son of the author, decided to enroll in a reading course that allegedly increases reading speed and comprehension. Prior to enrolling in the class, Michael read 198 words per minute. The following data represents the words per minute read for 10 different passages read after the course. Part A says, because the sample size is small, we must verify that the reading speed is normally distributed and the sample does not contain any outliers. The normal probability plot and the box plot are shown. Are the conditions for testing the hypothesis satisfied? Now, because they're giving us the plots here, we don't need to do this ourselves. And I would say on the basis of the normal plot, it looks like we're okay. The box plot is a little bit, a little uncomfortable. The main reason the box plot looks like it does is because when you look at the data table, you can see that there's this one value of 227. That's a very high value relative to the others. And we could check if it's an outlier, but I'm not going to. It's a little bit of a tangent, and so I don't want to bother with that. There may be reasons why that is there, and it's not a value to be discarded. For example, he may have been reading a passage that was very easy to read, with small words and so on and so forth. Anyway, it's normal enough for our purposes. So we want to test this claim here, because Part B is asking, was the class effective? In other words, did the kids' reading speed increase? So that's your alternative hypothesis in English right there, and that is that's a right tail test. Now I've taken the time to key in the data, as you can see right here. So let's go back to the stat menu and we'll run that test. Again, this is a t-test, and the reason is because we don't know the population standard deviation. So we take number 2, and this is a data-driven problem, so we need to change that. Mu naught, in this case, is his reading speed prior to the class. That's the reading speed according to the null hypothesis. So that would be 198 words per minute. The data is in list 1, and the frequency is always 1. Never change that. Now this is a right tail test, because the alternative hypothesis is basically that the reading speed's increased. So I'll select that, and then I'm ready to calculate. And here you can see the test statistic. It's 3.5049 and some change. And the p-value is also given. It's 0.0033, blah, blah, blah. Now the p-value is very small, and it's smaller than alpha, which means that we would reject the null in this case. And the import of that is that it looks like the class was successful. It looks like the kids' reading speed has increased. At least it's statistically significant. I don't know if it's practically significant, but that's a topic for a different day. Anyway, I hope these help, and in the next video we're going to have some more examples of hypothesis testing on the calculator.